It is my great pleasure to welcome you to the world of learning new concepts and current trends, so let's start. When you write code, you're building instructions for a perfect world. But the real world is chaotic. Files go missing, database connections drop, and users will inevitably type the word pizza into a calculator. If you misspell a command, your compiler catches that syntax error before the software ever ships. If you use the wrong formula, your logic error just gives the user a wrong answer. But then there are runtime errors. These are the failures that trigger live, right in the middle of execution. Take a look at this Java code. It's attempting an illegal operation, dividing 10 by 0. Without intervention, this single line immediately halts the entire program. The application drops dead and dumps this technical stack trace straight to the console. Both Java and Python give you tools to intercept these crashes. The catch is how you use them. Developers have to choose between a fast, flexible approach that might hide bugs, or a strict, verbose architecture that guarantees stability. Strategic exception handling is the only thing standing between a minor user error and a total application collapse. The baseline defense against a crash is simple. You test the dangerous code, and if it fails, you intercept that failure before the program terminates. Python handles this with a flexible try and except model. Java uses a similar try-catch structure, operating under tighter constraints. While both stop the immediate crash, Java forces you to understand exactly what kind of error you are trying to intercept. This requirement exists because Java organizes every possible failure into a strict architectural system known as the exception hierarchy. At the top of the tree is the throwable class, which splits into two branches, error and exception. Exceptions are routine problems you should catch and recover from, but errors represent cataclysmic failures that generally shouldn't be caught. If a method doesn't catch its own exception, the error gets thrown up the call stack. It moves up the chain to whoever called that method, searching for a catch block until it either finds one or crashes the program. By enforcing this rigid hierarchy, Java prevents you from treating all system failures as the same problem. It forces you to architect specific defenses rather than relying on quick fixes. This strictness often leads to a tempting developer shortcut, known as Pokemon exception handling. This is the urge to just catch the highest level exception to make the compiler happy. Writing a broad catch-all like this takes almost no typing effort, and it stops the immediate crash. The trade-off is severe. You create massive debugging blind spots by masking critical system failures right alongside trivial user input errors. The enterprise-grade solution in Java is to write multiple, distinct catch blocks, tailored for specific expected failures. Here, a single try block is followed by two sequential catch blocks, one for a math error and another for a data array error. The system checks these blocks one by one, executing only the first perfect match. This allows for distinct recovery behaviors and highly precise logging. Since Java 7, you can use the multi-catch operator, the pipe character, to handle several specific exceptions in one block without duplicating your code. Instead of dumping every problem into one bucket, you are routing unique error objects directly into specific matching safety mechanisms. Writing targeted catch blocks creates friction up front, but it drastically reduces maintenance time by pointing you instantly to the exact point of failure. There is one last component to Java exception handling that acts as the ultimate safety net, the finally block. Look at this scenario. The code throws a divide by 0 error, but the catch block is looking for an array error, missing it completely. Even though the program crashes, the finally block still executes 100% of the time. This is how you guarantee that vulnerable resources, like open database connections or file streams, are safely closed no matter what happens during execution. To see just how dominant the finally block is, consider this edge case, placing one return statement in your try block and another return statement in your finally block. The return statement in the finally block will completely override the successful result of the try block. To avoid creating bizarre, untraceable logic bugs, you should never use return statements inside a finally block. However, that absolute execution priority is what makes Java applications leak-proof, securing system resources even in the worst-case scenarios. The central trade-off throughout this process is development speed versus diagnostic clarity. We can map these techniques to evaluate the return on your effort. The Pokemon catch-all sits in the bottom left. It takes 0 effort to write, but it offers poor stability and 0 diagnostic clarity. Multi-catch plus finally sits in the top right. It requires high initial effort, but guarantees absolute stability and resource safety. For Python scripters and rapid prototypers, basic try-except chains are perfectly fine for straightforward data processing or temporary debugging, but production-level Java developers must abandon lazy catch-alls, embrace targeted exceptions, and mandate finally blocks for all external resources. Java's strict rules might look like frustrating boilerplate, but they function as architectural guardrails designed to prevent catastrophic failures when your code hits the real world.